talking about a problem that might just explain why your favorite LLM sometimes fumbles the simplest tasks. Ever asked an AI to count past 100 and gotten weird answers? Or copy a string only for it to glitch like a forgetful goldfish? Turns out transformers have a vision problem. No, really, they need glasses. In the latest episode of Machine Learning Street Talk, they interviewed Federico Barbero, the lead author of Transformers Need Glasses. They uncovered two major issues: representational collapse, where different inputs become indistinguishable, and oversquashing, which crushes critical details. These flaws make Transformers provably bad at tasks we thought were easy. But don't worry, there are simple fixes, and today we're breaking it all down. Let's get started.
Transformers have truly changed the game in natural language processing. They're behind those large models that predict the next word in a sentence with impressive accuracy. But there's a hidden flaw in these models that doesn't get enough attention. Sometimes, they just aren't sensitive to specific tokens in the input. We call this problem representational collapse. Different inputs can end up with nearly identical representations inside the model, almost like feeding various recipes into a food processor and getting the same mush every time. That's handy for some broad tasks, but disastrous when you need precision. Another issue comes from the low-precision floating-point formats these models often use. These formats can cause errors in tasks needing more exact distinctions. Imagine a calculator that always rounds to the nearest 10. This phenomenon ties into oversquashing, a term borrowed from graph neural networks, or GNNs. Oversquashing occurs when a lot of information is forced into a compressed space, so crucial details get lost. It's like cramming an entire book into one paragraph. The authors show theoretical and empirical evidence that this is happening in large language models. Does that mean transformers aren't amazing? Of course not. They're extremely powerful. But these flaws matter. The good news is that this paper proposes some ideas for addressing them. Look at the figures and equations on this page. Notice how they give a sense of the model's internal representations, and how certain tokens can get blurred together. Keep that in mind as we move forward, because we'll need those visuals to understand the solutions the authors hint at. We've just touched on the idea of representational collapse. Here, we see more details about why this is such a big deal. Transformers are excellent at language modeling in general, yet sometimes they fail in surprisingly simple ways. Representational collapse is one culprit. You give the model slightly different inputs, but it treats them the same internally. This issue is magnified by the lower precision floating point numbers in modern architectures. Small variations that should matter end up looking identical. Then there's oversquashing. Transformers pass information token by token, one after another, with previous tokens influencing the next. Think of the classic game of telephone, where the first message tends to morph by the end. By the time earlier tokens get through all those transformer layers, they might lose their original meaning. You can see examples of this in any figure showing attention weights across long sequences. The authors emphasize that external tools, like specialized modules or plugins, might offer a temporary fix but don't solve the heart of the problem. If the base model can't copy or count reliably, adding a workaround on top doesn't change its underlying limitations. As you read through the tables on this page, you'll notice how performance drops in tasks that require precise token-level fidelity. The authors show mathematical links to similar issues in GNNs, reinforcing that this isn't just a fluke, it's a structural problem worth serious attention. Now let's peek under the hood of the transformer itself. Check out the diagram here that illustrates how queries, keys, and values interact. Each token in your input gets a query vector, a key vector, and a value vector. Attention scores are computed by comparing queries and keys, then run through a softmax so they sum to 1. The output is a weighted sum of the value vectors, and that result becomes the token's updated representation. This process repeats across multiple layers, refining each token's representation. But keep in mind that standard transformers are causal. Each token only attends to those that came before it, forming a triangular pattern in the attention matrix. If you look at figure XXX, the triangular matrix illustration, you'll see that this leads to a directed graph-like structure through the layers. In the final layer, the model normalizes these representations. And for text generation, it's the last token's representation that drives the model's next word prediction. Many theoretical studies have asked, is a transformer basically a Turing machine in disguise? Some argue yes, especially if you replace softmax with a hard attention mechanism. Others see parallels to formal automata in the way recurrent networks mimic finite state machines. All this background sets the stage for understanding how representational collapse and oversquashing happen. Keep these fundamentals in mind as we dig into real experiments. Look at the examples laid out here on simple copying tasks. The model is asked to predict either the last or first token in a sequence of numbers. Sounds straightforward, right? But as the sequence grows longer, the transformer starts making mistakes. Researchers tried giving it some hints, little nudges in the prompt. That helped a bit, but not enough. Then they tried an alternating pattern of zeros and ones, making it tougher to memorize. The failure rate went up. Why is that so telling? It's not just the complexity of the sequence. It points to fundamental limits in how transformers pass information from layer to layer. Oversquashing rears its head here. In a GNN analogy, it's like messages passing through multiple nodes and losing clarity along the way. If you check out table XXX on this page, it shows how commute times, the measure of how far apart tokens are in representation space, grow with sequence length. More distance means higher chance of squashing. So, if transformers stumble on something as basic as copying, what other tasks are at risk? The authors tease that we'll see even more surprising failures in counting tasks coming up next. Keep your eyes open for more experimental results on the following pages. Counting is pretty simple. At least, that's what you'd think. You'd expect a big model like Gemini 1.5 to breeze through tasks like summing numbers or counting how many times a token appears. Yet the experiments here reveal that errors become frequent as the sequence length increases. Sometimes the mistakes are shockingly large. Researchers tested Gemini 1.5 on multiple tasks, summing numbers, counting sequences of ones, counting mixed sequences of zeros and ones, and even counting how often a word appears in a sentence. Turn to table XXX here. Notice how performance drops off sharply for longer sequences. Instead of tracking exact counts, the model starts guessing. If it sees mostly ones, it defaults to an inflated guess. This points to an information vanishing issue. Copying tasks showed something similar. When asked to recall the first number in a sequence, the model did okay. But copying the last number posed huge difficulties beyond about 300 tokens. Interestingly, adding a prompt nudge, like a specific reminder to pay attention, helped the model's accuracy. Using an alternating pattern, like 101010, also improved results. Why? Because it kept the model's internal representations more distinct. We're seeing a pattern. Transformers often lose track of information in the middle or end of long sequences. That's not just a minor quirk. It suggests a core architectural bottleneck. Here, the focus is still on counting, but now it's highlighted just how severe the problem gets as sequences lengthen. Gemini 1.5 stumbles in tasks that should be trivial, such as counting how many times a token appears. And the longer the input, the worse it gets. Table XXX in front of you shows that once the sequence length nears 100, the model often guesses 100, regardless of the true count. That's not actual counting, it's more like an approximate guess. This behavior, sometimes called subitizing, shows that the model isn't truly summing up tokens. The authors also found that if ones appear with a certain probability, like 70%, the model's errors grow more dramatic. Why? Because representational collapse is happening. After enough tokens, the internal states for different sequences start looking the same. When you see lines on a plot nearly overlapping, that's representational collapse in action. It underscores a major limitation in how transformers handle long inputs. If two sequences differ only by a token or two, the model might not distinguish them at all. Speaking of representational collapse, you'll see it formalized with two key results here. First, if two input sequences become increasingly similar, their final representations also converge until they're nearly identical under the softmax. Second, even a slight tweak, like repeating the last token, can make a transformer lose track of sequence differences. Check out theorem XXX to see the formal proof. It hinges on floating point precision. Once the difference between two sequences falls below a certain numerical threshold, the model lumps them together. This is disastrous for tasks that require token-level accuracy. When the authors tried tasks like counting the ones in a sequence with a repeated last token, collapse happened sooner, often around just 50 tokens. So it doesn't take an extremely long sequence to break the model's ability to differentiate. Quantization techniques, aimed at making models faster by reducing precision, only worsen the problem. And tokenization schemes can add more layers of confusion. A sequence of ones might not even be stored as separate tokens. An interesting workaround appears here, injecting extra tokens to maintain representational distance. It's a bit of a hack, but it helps keep sequences from blending together. Is that an ideal fix? Probably not, but it does show that we can do some practical tweaks to push back against collapse. Now let's look at how oversquashing ties in. Even if two different sequences don't collapse outright, Earlier tokens in the sequence might have their information squashed by the time it reaches the final layer. That's over-squashing, a phenomenon where the network effectively compresses or discards details from earlier positions. Observe the counting and copying experiments on this page. In counting tasks, like asking how many ones are in a sequence, representations get progressively collapsed. For copying, the model also struggles to retain precise tokens over long distances. But there's a simple intervention here: inserting commas or special tokens every few digits. That helps preserve differences between positions, partly preventing collapse. This over-squashing problem echoes the vanishing gradient issue in recurrent neural networks. Think of each transformer layer as a filtering step. If attention weights are skewed, some tokens get overshadowed. Look at theorem 5.1 in the margins. It's indication. It shows that the sensitivity of the final token's representation depends on both its position and the attention distribution. Uneven attention can worsen over-squashing. It's a structural limitation that doesn't just vanish by adding more layers or bigger models. Now you might ask, does position really matter that much? According to theorem 5.1, it does. Early tokens have multiple layers to feed their information forward, so sometimes they're better preserved. Tokens near the end have only one shot. If the attention at their layer downplays them, they basically vanish from the model's final representation. That explains the U-shape effect in performance. Transformers often do well at recalling the very first and very last tokens, while tokens in the middle can be neglected or altered. Counting tasks showcase another quirk. The softmax normalization used in attention can work against exact counting. Without explicit position embeddings or causal masks, the model has no direct handle on where tokens appear in the sequence. As a result, counting becomes exponentially harder for longer inputs. Even if a transformer can copy or do partial counting for short sequences, it struggles to scale up. Check out the graphs on this page to see how error rates climb steeply as sequence length grows. We arrive at the paper's conclusion. Transformers face two main limitations: representational collapse and over-squashing. Look at corollary 6.2 here. It states that even if a model generalizes well on smaller examples, counting tasks might remain impossible once sequences go beyond a certain length. This is largely because floating point precision eventually treats different sequences as the same, and the transformer architecture over-compresses earlier tokens. This framework explains a lot of those puzzling failures we see in large language models. The authors suggest new ways to measure over-squashing and track representational collapse as potential avenues for future research. By refining how information flows, we might finally overcome these architectural bottlenecks, or at least, we'll know better how to mitigate them. And that's the heart of it. Transformers are incredible, but they come with these inherent issues. By understanding representational collapse and over-squashing, we can spot failure points and hopefully work on better designs or training methods. Thanks for following along in this guided reading. Whenever you come across a table, figure, or theorem in this paper, think back to these core ideas, because they shape how well a transformer can handle long sequences and structured reasoning. Thanks for joining us today. Happy exploring!